Welcome back. In this section, we'll be talking about roots and rational exponents. So to begin with, talking about roots or radical expressions, another way for us to talk about them, a couple of things that we'll remember from the past, namely that if we're talking about things like odd roots, cube roots, fifth roots, seventh roots, and so on, that for any number, whether it's positive or negative or zero, that those roots will be real numbers. So cube root of -8, for example, that's a real number. That would be -2. And that's, of course, because -2 cubed gives us 8. When it's time to talk about even roots, square roots, fourth roots, sixth roots, and so on, it's only roots of numbers that are not negative, so 0 or things that are positive. Those would be real numbers. So for example, square root of 4 is 2, and that's because 2 squared is 4. However, any sort of a root of a negative number, so root of -3, you would say that that is not a real number. And remember that by real numbers, we're referring to all of the numbers that we use when we're doing any sort of measuring or counting. So this includes positives, includes negatives, includes fractions, includes decimals, includes any sort of a number that you would consider to be an actual number. Those are our real numbers. Now, there's a bunch of properties for these radicals. And so for some of these, you will remember these from days gone by. So for example, if we've got a root of some things multiplied together, you could write that as a product of those individual factors that are each under a root. Same thing for a fraction inside of a root. That's root of the numerator over root of the denominator. Here, of course, denominator can't be 0. And similar sorts of properties that we had for roots and powers combined together. So if I have something being raised to a power and then a root happening, that's the same thing as doing the root first and then doing the power after. All of this, of course, I didn't write any little side conditions here about a's and b's and what values they could take on. But of course, we're only thinking about things that are real numbers in this course. So if, for example, we were thinking about even roots, then hopefully we're thinking about numbers that are not negative. So I'm not mentioning that, but of course in the background of our mind we should be thinking about these sorts of things. For part 4 here, I've got a little side note, which is that what happens if you have a power of n and an nth root being combined together? They do cancel each other out to an extent, but there is a little bit of a plot twist here. And that's if you're talking about odd powers, so cube root of something cubed, those will cancel each other out just nicely. So any number cubed, taking cube root, you get your original number back. If we're talking about even powers, on the other hand, I say it's the absolute value. And that's because, of course, when you raise something to an even power, that makes the whatever that number is something that's positive. That's the reason why here we don't have to worry about is this a real number or not. If n is an even power, even if this were negative, a to the power of n would turn out to be something positive, and then of course you can take roots of positive numbers just fine, and what you'll get will be a positive value. So no matter whether a is positive or negative, if we have an even root and an even power, the same number being for both, then we'll get an absolute value of what was on the inside. So as an example of that, if you're thinking about -3, if you were to square that and then square root it, -3, when you square it, you would get +9, and when you square root 9, you get 3. So here, the squaring and square rooting don't really cancel each other out. You don't really get -3 back. You got the absolute value of -3. You got +3. I have here as an in general, this is true for roots, but actually it's true for any power, not just for roots as well. So this is something to keep in mind, that also if you're thinking about two things added together and raised to a power, That's also not the same thing as power on the first thing plus power on the second thing. That's another little fact to keep in mind. It would be lovely if things worked out that way. That might make some of our algebra easier to do, but unfortunately that's not how it works. These are not properties of powers or of rational expressions. So when we've got things that are products or quotients, yes, we can go splitting them up, but for things that are sums or differences, adding or subtracting, nope, sorry, we cannot. Now, remember from before that when we're talking about simplifying a radical expression, you have to make sure of a couple of things, and one of them is that there are no perfect whatever that kind of power is. If it's a square root, no perfect squares. If it's cube roots, no perfect cubes. You don't want any perfect squares to be stuck inside of a square root. You don't want any perfect cubes to be stuck inside of a cube root. So for example, you wouldn't say square root of 4, you would say 2. That would be the way to simplify it. Or if you had something like square root of 8, although square root of 8 is not a perfect square, 8 is not a perfect square, 8 is a perfect square times another number. 8 is 4 times 2. You could say that root of 8 is root of 4 times root of 2, or 2 root of 2. This is what I mean by extracting these perfect squares from these roots. This is something that's required for us to do when I want to give something that's in simplest terms, that's a radical expression. I need to make sure that I've taken out any of those perfect squares, in this case, out of that root. So this is something that I'll expect to see for the entirety of this course. Something like square root of 8, I would not consider that to be a simplified answer. I want to see 2 square root of 2. So for all of these, I'll do my simplification. And these, I can say that none of these numbers, 75, 20, 12, 45, none of those are perfect squares. However, they do have perfect squares inside of them. 75 is 25 times 3. 20 is 4 times 5. 12 is 4 times 3. 45 is 9 times 5. And I could say, and I'm not going to do all the writing here, I could say that root of 25 times 3 is root of 25 times root of 3, and root of 25 is 5. And same thing with the next term, and the next term after that, and the last term after that. And now I can see that I've got some terms that have roots of 3's involved. I can combine those together. I've also got some terms that have roots of 5's involved, so I can combine those together. I have 5 root of 3 and 2 more root of 3's, so I've got 7 root of 3. I've got 2 root 5 plus 3 root 5. I have 5 root of 5 all together. And I can say here that there's nothing further that I can do to simplify this. There are no perfect squares that can be taken out of either of those roots. I've already done that. I can't combine those two terms together. One of them is in terms of roots of 3, the other one in terms of roots of 5. So I've done as much work as I can do. For the next one, I'm going to see that I've got one thing multiplied by another, so I'm going to need to expand. And when I do that, I'll multiply out each term from the first bracket by everybody in this second bracket. That's the plan for this. So I'll start off by multiplying 2 root of 3 times 5 and 2 root of 3 times 2 root of 3. So 2 root of 3 times 5, the 2 and the 5 multiply together to give us 10. And the root of 3 comes along. For 2 root of 3 times 2 root of 3, 2 times 2 is 4. Root of 3 times root of 3 is 3. So we'll be left with 4 times 3. I'll simplify that after, but that's what we have for now. Remember that when we're multiplying things out that involve radicals, we would be multiplying the whole number parts together. We'd be multiplying the radical parts together. So when you take 2 root of 3 and multiply it by 2 root of 3, The 2's multiply together to give you 4. The roots of 3's multiply together to give you 3. And so you're left with 4 times 3. All right, so next we've got negative root of 2 times 5. That would be negative 5 root of 2. We have negative root of 2 times 2 root of 3. That's negative 2 root of 2 times 3 is 6. Remember that when we're multiplying roots together, we're going to multiply their insides together. So root of 2 times root of 3 is root of 2 times 3, or root of 6. And then the last thing that I'll need to do is just that one bit of simplification of 4 times 3, having that be 12. As far as what's left over, I can see that for all of the roots that are there, root of 3, root of 2, root of 6, none of those have any perfect squares that can be taken out. There's nothing else that I can really do to combine these terms together, so I am finished. Now for something like this, I have a couple of options as to how I can simplify things, and one thing that I might consider to do first is just to simplify what's inside of that root. Because if I'm taking a look at the root itself, I have in the numerator 24 and in the denominator 3, and 3 goes into 24 just nicely. It goes into 24 8 times. Similarly, I have x to the power of 4 over x, which is the same thing as just x cubed. So really, if I were to simplify things inside that root, it simplifies out to give me root of 8x cubed y cubed. And now as far as perfect squares go, when I say taking perfect squares outside of a square root, I don't just mean the numbers that are perfect squares, I also mean the variables that are perfect squares. So 8, we already talked about that before, that's 4 times 2, and 4 is a perfect square. But with x cubed, there's a perfect square inside of that as well. X cubed is x squared times x. And same thing with y cubed, that's y squared times y. So that means that the 4, the x squared, the y squared, those are all perfect squares that could be taken outside of my square root. Square root of 4 is 2. Square root of x squared is x. Square root of y squared is y. So I've taken all of those squares out, and what's left behind? I've got the 2, the x, and the y. Rationalizing the denominator is something, again, that I'm going to expect to see as part of what does it mean to have something in simplest terms. When I say a rationalized denominator, I mean that if there are any roots, that there shouldn't be any roots in the denominator, and that we'll need to move all the roots, whatever ones that there are, to the numerator of our rational expression. Now, one thing I do want to say that there is going to be one exception to this coming up, and this is going to be a little bit further into the course. So with the one exception, and that exception being the difference quotient, when we talk about the difference quotient, that will be the one exception where it will be okay for you to leave roots in the denominator. But for everything else, and that's not just at the beginning of the course, this will come back again towards the end when we talk about trigonometry. There's lots of square roots in there as well. Those roots as well would also need to be written in such a way that if they're in a fraction, that they're not in the denominator. Now, there's two options as to what we can do, depending on what the denominator looks like. It'll either be something where we have one single term in the denominator, or we might have two terms in the denominator. Here, this is one where I've got one term, and to rationalize the denominator when there's only one term, we would just multiply top and bottom by that one term, in this case multiplying top and bottom by root of 8. And that simplifies us in the denominator, because in the denominator, root of 8 times root of 8 would just be 8. For the numerator, we have to remember that both terms, not just the root of 7, but both terms are going to be multiplied by the root of 8. Root of 8 is going to multiply by root of 6 as well as by root of 7. So what do we have in the numerator? We have root of 6 times root of 8, or root of 6 times 8, which is 48. And then we have root of 7 times root of 8, which is root of 56. And now, even though we've rationalized our denominator, we're not necessarily finished yet. We'll still need to ask ourselves the question of, are the roots themselves in simplest terms? Are there any perfect squares that can be taken outside of that root? And that's the next question that we'll need to ask ourselves. So for 48, one thing that you'll notice is that 48 is the same thing as 16 times 3. So 16, or 4 squared, that's the perfect square that can come on out. So root of 48 is root of 16 times 3, or root of 16 times root of 3. For 56, if we were to look at what perfect squares go into that, 4 goes into 56, and 4 goes into it 14 times. So root of 56 is root of 4 times 14, or root of 4 times root of 14. And now the one last thing that I'll do here is to note that for the numerator, I could factor 2 out of everybody. 2 is a factor out of the first term and out of the last term. And that's the reason why I'll be able to cancel 2 from the numerator as well as from the denominator. 2 goes into itself once and into 8 4 times. So that really what we'll have in simplest terms, 2 root of 3 plus root of 14 all over 4. Now, the one thing I do want to also point out, although I was able to cancel out 2 and 4, 2 from the numerator and the denominator, you might be tempted to try to do it again and say, well, can't we cancel this 2 out with this 4? And if you're thinking about doing that, resist that urge. Because remember, for us to be able to cancel something from the numerator and the denominator, it needs to be a factor of the numerator and also a factor of the denominator. This factoring was okay for us to do, and that's because 2 was a factor that got taken out of the entire numerator, and 2 could also be taken as a factor out of the entire denominator. On the other hand, here, 2 is not a factor of the entire numerator. 2 can come out of the first term, but there's no 2 to come out of the second term, and since 2 can't be factored out of the entire numerator, then I can't cancel 2 out. So, therefore, I am finished. I can't go any further. Now, for something like this, where it's not one term, where it's 2 terms in the denominator, this is where we're going to use our difference of squares identity. Remember that when you have a minus b times a plus b, when you have something multiplied by its conjugate, when I say things that are conjugates, I mean that they're the same except for they have the opposite sign in the middle. Those two things, a minus b and a plus b, I would call them conjugates. When we multiply something by its conjugate, we get the first thing squared minus the second thing squared. And if that was a root or if that was a root, either way, I wouldn't have any roots left over at the very end. So that's kind of our idea here, is that if we have 2 terms in the denominator, we're going to multiply top and bottom by whatever the conjugate is. So here, the denominator is root 6 minus 3 root 2, so I'll multiply top and bottom by root 6 plus 3 root 2. The same sort of caution that I said before, I'll mention it again here, namely that the entire numerator root 6 plus 3 root 2 is going to be multiplied by this entire numerator of root 10. So it's not just going to be the root 10 times the root 6. The root 10 will also be multiplied by the 3 root of 2. As far as the denominator goes, we already know what the denominator will turn out to give us. It will give us the first thing squared minus the second thing squared. That's exactly what we have there. We are using that difference of squares identity. A minus b times a plus b gives you a squared minus b squared. For the numerator, I'll multiply that out. Root 10 times root 6, that's root 60. Root 10 times 3 root 2, that's 3 root 20. And now the only things that are left to do are to simplify my roots, simplify the denominator, and then we're pretty much finished. I'll do the denominator first here. So we have root of 6 squared, which is 6. And then we'll have 3 root of 2 squared. And when we say 3 root of 2 squared, that would be 3 squared times root of 2 squared, which would be 9 times 2, which is 18. So 3 root of 2 times 3 root of 2, that's 9 times 2, or 18. For the numerator, root of 60 and root of 20, those both have perfect squares that can be taken out of them, namely 4. 4 goes into 60 15 times, so root of 60 is 2 root 15. And 20, 4 times 5 is 20, so 4, that's the perfect square that can be taken out. So we'd have 3 times root of 4, which is 2. 3 times 2 is 6. There we go. So 6 root of 5 is what we've got left over. I just need to clean up my denominator, and then we're pretty much finished. I have the denominator is negative 12. And now I can see that if I'm looking at the numerator, 2 and 6 are the whole number parts, and both of those numbers are divisible by 2. The denominator is also divisible by 2, so I could cancel out everybody, divide everybody top and bottom by 2. So root of 15 plus 3 root 5 over negative 6. One little last one to do, just as another example. If I were looking at root of 6 divided by 4 plus root of 3, and I want to rationalize that denominator, I will multiply top and bottom by the conjugate, 4 minus root of 3. And so that in the denominator, I would get first thing squared minus the second thing squared. I've taken a plus b and a minus b, and I multiply them together to give me a squared minus b squared. For the numerator, that 4 minus root of 3 is being multiplied by root of 6. So 4 times root of 6, that's 4 root of 6. Root of 6 times root of 3, that's root of 6 times 3, which is 18. And now the only thing left to do, just to clean things up, the denominator, 4 squared, that's 16. Root of 3 squared, that's 3. And for the numerator, we've got 4 root of 6. Root of 6, that's in simplest terms. That can't get any simpler than that. But root of 18, there is a perfect square that goes into 18, and that would be 9. 9 goes into 18 twice, so we would have root of 9, which is 3 times root of 2. And now, last thing for me to do, just to simplify my denominator, I have 16 minus 3, or 13.